Hi, this is Al, your probability and statistics instructor. Let's begin doing probability. Okay, so today, in this short video, we will discuss only one concept, the concept of independence. Okay? Our discussion will begin with the definition of independence. Two events A and B are said to be independent if any one of the following holds. Okay? If the probability of A given B equals the probability of A. Think about it. What we're saying here is that the occurrence of the event B doesn't change the probability of A. Make sense? Something similar happens here. If the probability of A given if the probability of B given A equals the probability of B, that means that the occurrence of A doesn't change the probability of B. Okay? Finally, a third way of checking that two events A and B are independent. If the probability of A intersection B equals the probability of A times the probability of B. Okay? If these relationships don't hold, then what we say is that the events A and B are dependent. Okay? So you can check any of these three. If any of these three hold, then A and B are independent. Make sense? Okay. Let's talk about an example. Okay? So we have a population. We have 60% of them own a car, 30% of them own a house, and 20% of them own a house and a car. Okay? So what we would like to know is whether or not these two events are independent, owning a car and owning a house. Okay? So let's set it up. First, let's define the event A as a person owns a car. Event B, a person owns a house. And, well, A and B, a person owns a car and a house. Now let's go back to the information that we have. We have the probability of A is 60%, probability of B 30%, and probability of A intersection B is 20%. Okay? Okay, here we go. probability of A equals 60%, probability of B equals 30%, and probability of A and B, probability of the intersection, is 20%. Now note that probability of A times probability of B equals 0.6 times 0.3, that happens to be 0.108, and clearly 20% is different from 18%, which is the product of A, well, the probability of A and the probability of B. So in this case, given the information that we had, it was a good idea to use this expression, checking the third condition, that the probability of the intersection was different from the probability of the A times the probability of B. Make sense? In other problems, perhaps using either the first one or the second condition that we had for the to check independence might be a better idea, okay, in some other problems. But in this particular case, it was a good idea to use this one to check whether or not A and B were independent. But in this case, since this relationship doesn't hold, what we have is that A and B are not independent. Okay, so let me just say that. Therefore, A and B, those events, are not independent. And that's it. Now, I would like to ask you something. What if you try to do this one as a homework problem? Okay? So, example about workplace accidents. Homework. Give it a shot. Okay? It isn't that hard. But I want you to give it a shot. Now, a final comment. We have three different ways, three different expressions to show that A and B are independent. But I want you to see that the third one is basically a consequence of one of the first two. Okay? If we assume that probability of A given B equals probability of A, then let's see what happens. By definition, you guys remember what's the formula for the probability of A given B? it looks like this, right? A given B, the probability of A given B will be the probability of A and B divided by the probability of B, right? That's just by definition. Now, since by assumption we have that probability of A given B equals this, what we have is that this expression equals probability of A. Oops. And that's just by assumption. By assumption. And then if we solve for the intersection, or multiplying by probability of B on both sides, what we have is that probability of A and B equals probability of A times probability of B. See? So we were able to derive the third expression, or the third way of checking that events A and B are independent. Okay, so you could do the same with this one, right? So all of them are equivalent, and you need to check only one of them, not all three, one of them. Okay. Okay, so summary. What we talked about today was conditional probability, independence, and remember we have these three different ways of checking that A and B are independent, and all of them are equivalent. Probability of A given B equals probability of A, then A and B are independent. Probability of B given A equals probability of B, then A and B are independent. And or if the probability of A and B, the probability of the intersection between A and B, equals the probability of A times the probability of B, that's it. You have shown that A and B are independent. It is just that simple. Okay? Well, that's it for now. Take care and keep working hard. See you next time. Bye.